how do you spark a chemical revolution without, burning down the planet? It's honestly one of the most high-stakes questions of our modern era. We desperately need to invent new, sustainable ways to produce everything from life-saving pharmaceuticals to clean energy. But we've got to do it faster than ever before. And we have to do it without generating mountains of toxic waste or relying on these massive fossil fuel-burning furnaces. Sounds completely impossible, right? Well, the answer actually lies in a microscopic hero, the catalyst. And that is exactly what we're going to explore today. Welcome to this explainer. I am literally so excited to dive into this one with you. Today, we're looking at the Alchemist's digital twin, AI, catalysts, and the future of green chemistry. We're going to unpack exactly how cutting-edge artificial intelligence is merging with foundational chemical science to just completely redefine how we discover and manufacture materials. So if you love understanding how complex systems become hyper-efficient, you are definitely in the right place. Here's a quick look at our roadmap for today. 1. The magic of catalysts. 2. Driving sustainable green chemistry. 3. The discovery bottleneck. 4. Enter artificial intelligence. And finally, 5. The autonomous future. All right, let's jump right in with Section 1. The magic of catalysts. The unsung heroes.
Okay, so to really grasp this AI revolution, we first have to understand what the AI is actually trying to optimize in the first place. Fundamentally, a catalyst is like a chemical matchmaker. It's a substance that lowers the activation energy needed for a reaction to even happen. Think about a standard piece of wood, right? It won't just spontaneously react with oxygen and start burning on its own, which thankfully is great, or else our entire planet would just be on fire. It needs an initial spark. That spark is the activation energy. Catalysts essentially act like a chemical shortcut, drastically bypassing that massive energy requirement so these reactions can happen super easily, super quickly, and at much, much lower temperatures.
But here's their absolute superpower. They don't get used up in the reaction itself. They facilitate the chemical change, forcing the molecules together or pulling them apart, and then they just detach, completely intact, ready to do it all over again millions of times. Catalysts really are the ultimate reusable tools at the molecular level.
Moving right along to Section 2, driving sustainable green chemistry a global scale.
Now, this isn't just about making lab experiments run faster. Catalysis is the absolute backbone of moving away from petrochemicals and actually building a sustainable future. Historically, chemists really struggled with the trade-off here. Homogeneous catalysts had amazing activity, but they floated around in the exact same liquid as the reactants, making them a total nightmare to separate out later. On the flip side, heterogeneous, solid catalysts were super easy to filter out, but they just weren't as active. Nanocatalysts started to bridge that gap, but single-atom catalysts, or SACs, are the real massive breakthrough. By taking individual metal atoms and dispersing them onto a support material, we achieve what's called ultimate atom efficiency. Basically, it ensures not a single speck of incredibly precious metal is wasted.
Optimizing these catalysts is the key to unlocking what chemists refer to as the zero-waste paradigm. Put simply, this means vastly cleaner manufacturing for the everyday products we all use. With exactly the right catalyst, we can finally ditch those hazardous 500-degree industrial furnaces and actually run reactions at room temperature just using water. We can break down really tough renewable feedstocks like plant waste into biofuels without having to compete with the global food supply. We can even integrate it directly with carbon capture. It's a total transformation of the industry.
Which brings us to the core problem in Section 3, the discovery bottleneck, the slow search.
So, if catalysts are really that amazing, why haven't we solved all our green energy problems yet? Well, it's because the traditional approach relies so heavily on human chemical intuition and just incredibly slow trial and error. The parameter space of all possible chemical combinations is astronomically large. It's honestly like looking for a molecular needle in a haystack the size of Jupiter. Doing it the old way, it can take a decade and billions of dollars just to find one single perfectly optimized catalyst. But the AI-driven approach, that changes the whole game. Instead of just guessing, we can now leverage deep neural networks to rapidly screen massive virtual databases in a fraction of the time.
We're basically witnessing a complete paradigm shift right now. Historically, empirical rules led to this agonizingly slow manual catalyst screening. Today, machine learning and deep learning step in. We're using computational models to instantly predict how a catalyst is going to behave before we ever even synthesize it in the real world. We are entirely replacing blind trial and error with data-guided precision.
All right, Section 4, enter artificial intelligence, the new sidekick.
Advanced data science has officially become the chemist's ultimate sidekick. And it's directly solving that massive discovery bottleneck we just talked about. For years, scientists relied on computational chemistry, specifically quantum mechanical methods like density functional theory, to simulate molecules. Now that's highly accurate, but it demands insane amounts of computing power, so it's brutally slow. But when you feed that high-quality physics-based data into a machine learning algorithm, the AI actually learns the underlying patterns. Suddenly, it can predict outcomes for catalysts in energy and pharmaceuticals without needing to run those heavy supercomputer calculations every single time.
And the result of all that? Get this, 100,000 times. That is the staggering speed increase we are seeing here. AI models using neural network potentials can test virtual catalysts 100,000 times faster than ordinary, computationally heavy quantum calculations. Literally, what used to take a supercomputer months to figure out, an AI can now predict in just seconds.
And because of that mind-blowing speed, we can now build a fully closed-loop discovery process. It goes like this. First, generative AI, kind of similar to the tech behind ChatGPT, but for molecules, proposes completely novel catalyst structures that a human brain might never even think of. Next, machine learning instantly screens these virtual candidates, immediately throwing out the bad ones. And finally, the very best candidates are sent directly to automated robotic platforms that physically synthesize and test them in real life. Those results are then fed right back into the AI, making it smarter and faster with every single cycle.
No, this is crucial. This loop enables something called inverse design. Normally, right, you make a chemical and then you test it to see what its properties are. Well, inverse design completely flips the scientific method on its head. You start with the solution. You literally tell the AI, hey, I need a catalyst that converts carbon dioxide into green hydrogen, works at room temperature, and doesn't degrade over time. The AI then works backwards to design a brand new, custom molecular structure that perfectly matches your exact specifications. It's almost like magic.
And that leads us perfectly into our final section, Section 5, the autonomous future, digital twins.
So, we've talked a lot about discovering the perfect catalyst, right? But how do we actually scale that up to manufacture millions of tons of green chemicals? The answer there lies in the concept of the digital twin. A digital twin is basically a perfect virtual mirror of the physical chemical plant. Everything, from the microscopic catalyst behavior to the temperature of the vats, right down to the flow of raw materials, is modeled in real time by AI. It tracks incoming material quality and automatically adjusts chemical recipes on the fly to catch and prevent errors before they even happen on the factory floor.
And this isn't just some theoretical concept. Real-world chemical manufacturing giants, we're talking BASF and Dow, are already piloting these digital twin systems. By using AI to predict deviations and simulate plant transitions, they are seeing up to a 30% to 50% reduction in unplanned downtime. That is a massive leap in efficiency, and it translates directly to safer manufacturing and far cheaper, greener products for all of us. Just to quickly summarize how fast innovation is accelerating everywhere right now, large language models are actively out there mining millions of dense scientific patents. Global initiatives are standardizing chemical data so it can actually be shared and reused worldwide. We've got automated robotic labs running upwards of 10,000 physical tests a day, completely on their own, all seamlessly guided by AI models tracking reactions from the atomic level all the way up to industrial pipelines. Which leaves us with this final, honestly thrilling thought. We are fully transitioning from empirical guesswork to intelligent, data-driven creation. The old barrier of slow trial and error has completely been broken. So, when AI and autonomous robotic labs finally take the wheel completely, what impossible molecule will we discover next? Could it be a catalyst that just effortlessly eats up plastic waste, or maybe a material that perfectly stores solar energy forever? The tools are officially in place, and the next chemical revolution has truly begun. Thank you so much for joining me on this explainer, and as always, keep learning.